So thanks for the invitation and the introduction and for this opportunity to give this talk. So what I'd like to do is not actually talk about search in social media, although if there are any questions about this I'd be happy to try and answer them, but talk about some recent work that we have been doing in Amsterdam around this theme of adapting rankers online while the search engine is interacting with users. Okay, so before I start, I want to point out that this is joint work with my PhD student Katja Hofman and my colleague Simone Weitzen. So Katja works on this interface of machine learning and information retrieval. Simone Weitzen is a machine learning person, specifically reinforcement learning. I myself, I'm more an information retrieval person. Okay, so let me give you a bit of motivation. So, as you probably know better than I do, these search engines become more and more complex, using more and more features for ranking. A lot of work, a lot of research has gone into developing methods for optimization offline. What we'd like to do and what we're exploring right now is methods for learning online. So there's actually no distinction between training and optimization. Sorry, between training and operating. The search engine observes the user's interactions, the natural interactions, and tries to infer information from these interactions and then improve the ranking function automatically. So we don't require any expensive data collection. The data that we collect is simply represents what users like, what users do with the search engine. It's the target users in the target setting. Okay, so this is what it's about, observing users' natural interactions with the search interface, picking up signals from these observations and try to adapt as we go along. Now, this idea of picking up signals from users while they are interacting with the engine, that's not a new idea. So over the past decade or so, and even before that, this has been looked at quite extensively. So here's a map of different types of natural interactions, implicit feedback, originally introduced by Ord and Kim in about 10 years ago, and then adapted later by Kelly and Tevan. So what do you see here? The different categories of behavior. So examine results, retain them, reference them, annotate them, create them. That's along this axis. Along the other axis, what do we got? The minimum scope. So that refers to the smallest possible scope of an item that's being acted upon. So you can retain a segment of text by printing it. You can retain an object by bookmarking it, saving it. You can annotate a class of objects by organizing it into different subclasses, for instance. Right, so these are different types of natural interactions with the search engine that people have looked at over the past decade, and from which we've tried to make some inferences. Now, relevance feedback, that's probably an idea that you all know. Relevance feedback is an idea that goes back 40, maybe even 50 years. And in the past it has typically been used for query expansion, so taking an initial query, revising it, expanding it, reducing it, adjusting weights. It has also been used for profiling users. Now in the setting where we have explicit feedback, what are we dealing with? Well, there could be keywords, could be users selecting documents, marking documents, users asking questions about the results, answering questions about the results. Now, getting natural explicit feedback, so really users giving explicit feedback in a natural setting, that's not always easy. In a sense, we as researchers get unnatural feedback through events such as track and clay and NTCAR, where we have assessors giving judgments, giving the explicit feedback, or nowadays where we use the crowd to come with these explicit judgments one way or another. Now, I'm telling you this to contrast with the situation that we're interested in here. So implicit feedback. We want to use implicit feedback for learning, for query expansion, for user profiling. So what's at stake here? We observe users while they interact with the system. We look at things like what I showed you in the big table, reading time, whether they save an item, whether they print it, bookmark it, forward it, share it, select it, click on something, these sort of signals. If you read the literature and if you follow your own intuitions, and those types of signals are less accurate, are believed to be less accurate than explicit measures, explicit signals. But we've got them in very large volumes, or you've got them in very large volumes at no cost. And as researchers, we get them occasionally too. Okay, so this is our ambition, to use online learning to rank approaches, so that retrieval systems can learn directly from the implicit feedback while they're running. And I want to touch on two issues related to this. Here's the first one. So algorithms need to learn. How do they do that? Well, they need to explore new solutions. At the same time, they've already learned something. If we're in this online setting, they've already learned something, something that was hopefully reasonably acceptable for users. So we need to somehow exploit and make good use of what we've learned so far, but at the same time experiment, try out new things without disturbing our users too much. We don't want them to run off. So that's one of the two themes I want to touch on. The second of the two themes I want to talk about today is this issue here, interleaved comparison methods. So comparisons of ranked lists of rankers. We want to use implicit feedback to detect small differences between the rankers and to use this to learn ranking functions online. Okay, so the two themes: exploring and exploitation, trying to understand that balance a bit better, and these interleaved comparisons. And trying to use clicks, the implicit signal, to infer which of the rankers is to be preferred. Okay, so those are the two agenda items for this talk. This idea of balancing exploration and exploitation, and the idea of inferring preferences for one ranker over another ranker using clicks. Now, the first item is material that we've published recently at the European Conference on IR. The second item is ongoing work, and we've submitted a first part to a conference. Okay, so let's talk about this balancing issue. What are the challenges? Well, what we want to do when we're trying to learn online is to generalize over queries, generalize over documents. There's been lots of work in the literature where learning to rank has been applied for specific queries or specific documents or document collections. We'd like to generalize over these queries and over the documents. Moreover, we want to learn from implicit feedback. The implicit feedback clicks, it's noisy, it's relative, and it's rank biased. Items ranked higher have a certain bias of being clicked on before items ranked lower. And the third challenge here is for effective learning we need to explore, we need to try out new things, but we can't go crazy here. We need to keep our users happy while we're learning. What we're doing is we're learning document pairwise preferences, and we try to infer these preferences from clicks. So here's a query Vienna. We've got some results here. A ranked list, part of a ranked list produced in response to this query, and we got a click not at rank 1 but at rank 1, 2, 3, 4, 5. Now, how do we want to learn these document pairwise preferences? Our input consists of feature vectors constructed from document pairs. Our output consists of these two values, -1 or +1, whether two documents are in the right order or the wrong order. So this is an idea that was proposed by Torsten Joachims in a paper at KDD nearly 10 years ago. The learning method that he used in this setting was supervised. Several approaches were tried. I think certainly SVMs were tried in that paper. So we go to our challenges again. Yes, this can generalize over queries and documents. Yes, we can learn from noisy and relative feedback, but there is a strong rank bias here. So to correct for this, in a later paper, you and Joachims looked at the problem as a dueling bandit gradient descent problem. So we learn a ranking function that consists of a weight vector for a linear weighted combination of feature vectors from feedback about relative quality of rankings. What does that mean? So this is the intended outcome, a weight for the ranking. What is the approach? We maintain a current best ranking function that we've learned so far. We get a new query. We generate a new candidate ranking function for this query. We compare it to the current best ranking function, and if the candidate is better, we update the best ranking function. Now, in that, so that was, sorry, that was an ICML paper of 2 years ago. So this generalizes over queries, over documents. It can deal with the noisy implicit feedback with relative judgments rather than absolute judgments. It can correct for rank bias, but the way it was set up, it would explore a lot, try out new things, and there was a big risk in making users unhappy in that respect. Okay, so what we want to do is these two things. We need to learn effectively from rank biased feedback. That's why we need to explore. We need to present high quality results while we're learning, so we need to exploit, make the best possible use of what we've got. And the issue is to balance this. And previous approaches in the literature were either purely exploratory, basically learning very little as they went along, purely exploitative, learning very little as they went along, or purely exploratory, taking big risks in terms of making users unhappy. So the questions that we try to address in this ECAR paper were those: can we improve online performance by balancing exploration and exploitation? And actually, how much exploration is needed for effective learning? Okay, so we formulated this as a reinforcement learning problem with no explicit labels, and we learned from feedback from the environment in response to actions. So what is an action in this case? Well, an action is the retrieval system trying something, producing a ranked list of documents. What is the feedback of the environment? That's the user providing clicks. So our method is based on the Dueling bandit gradient descent that I sketched before, right? You maintain a current best ranking and you adjust it if the ranking that you produce in response to a new query turns out to be better. So we've got relative evaluations of quality of two document lists. And we infer comparisons from implicit feedback, from the clicks. Now let me explain that last bit. So it's a method we call K-greedy exploration. So to compare two document lists, what do? We've got one document list and another document list. We interleave them with a certain exploration rate, K. So that influences the relative number of documents from each list. So that's the ranking produced according to our current best ranker. That's the alternative list produced by an alternative ranker, and we interleave them. So let's take a blue one, a purple one, blue, purple, etc. That would be one way of interleaving them, and this would have an exploration rate of 0.5 because half of the results shown come from the alternative ranker. Okay? And if we then observe clicks on this interleaved list, and if both of the clicks land on results that come from the blue ranker, then blue wins. Okay? Here's another way. Again, we have our current best ranker, blue, the alternative ranker, purple. We could interleave them in this way: blue, purple, and the rest blue. This would have an exploration rate of just 0.2. Only 2 documents out of the 10 come from the alternative ranker. So we're exploring a lot less. We're relying much more on what we've learned so far. Okay, so how do you evaluate this? How do you determine what exploration rate is better. Now we used simulated interactions. What we need is we need to be able to observe clicks on arbitrary result lists, and we need to be able to measure online performance as we go along. So we simulate the clicks and measure the online performance using a probabilistic click model, the so-called dependent click model. For this we need to define click probabilities, stop probabilities, and we do this based on standard learning to rank datasets that have been made available to the research community over the past few years. And then we measure cumulative reward of the rankings that are being displayed to the user. So let me try and make that a bit more concrete. So I want to tell you a bit about these experiments here, where we vary the exploration rate, how many results come from the alternative ranker. We look at 3 click models with a perfect user, a navigational user, and an informational user. And we evaluate on 9 data sets taken from these learning to rank data sets, LITOR 3 and 4. These are 9 data sets. I think 8 are based on web search, and 1 is based on domain specific search, biomedical. Okay, so I'm going to show you 3 pairs of slides. Each pair looks like first a slide like this and then a big table. What I do on this slide here is I set the click model, and then I'll walk you through a graph. What is a click model? Well, the probability of a click given a relevant document, a click given a non-relevant document, stopping, the user stopping on a relevant document, and the user stopping on a non-relevant document. These are parameters that this dependent click model has. So these are parameters where we need to make a choice, and here we've got the perfect user who will just go on searching and will only click on relevant results. So yes, it's not realistic, it's an upper bound of what we may hope to achieve. Right? This user makes no mistake, doesn't click on non-relevant items, and has infinite energy, just keeps on searching and clicking. That's the model. These are graphs for one of those 9 data sets in the LITOR collection. What have we got? 3 curves for 3 levels of exploration. So k equals 0.5, that means half of the results come from the alternative ranker, so we're really exploring, really bringing in new results. K equals 0.2 is only 2 out of 10 from the alternative ranker, and K equals 0.1, that's a very careful degree of exploring. Only 1 out of 10 comes from the alternative ranker. Here we see the number of queries. This is NDCG. This was repeated, I need to look it up in the paper, either 100 times or 1,000 times over different sets of queries and averaged over this. So what do you see? Well, we learn a lot, and we do so very quickly. Right? We go from about here to NDCG of well over 0.6 with just a few hundred queries. Now, this is a big table. We're not going to walk through all of the cells, don't worry. What have we got here? The different sets that make up the Litor data set, the different exploration rates, right? Explore a lot, less, 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 and even less. What else have we got? We've got various shades of blue. The darker the shade, the higher the performance. If you see a box around a cell, that means we've got a significant difference over the explorative baseline. Okay, so what the take-home message is, the exploration rate of 0.2 apparently does best for this perfect user. So only explore with only 2 results in the top 10. Now a slightly different user model, the navigational model. So still a high probability of clicking on a relevant result. There's also a bit of a probability of clicking on a non-relevant result, and we've got various non-zero stop probabilities after a relevant result or after a non-relevant result. What do you see? Well, these curves here look very similar to the previous curves. They take a bit longer to achieve the same level as on the previous slide with the perfect user model. In the table we see some changes arising. Remember, in the previous table this was very dark blue. Now we see a bit of a shift to, well, exploring even less, 1 out of 10, and in 1 or 2 cases exploring a bit more. But on the whole, the take-home message here seems to be that you get the best performance with just a little exploration and lots of exploitation. Now, the third one I want to talk to you about is a very noisy interaction model. Still a high probability of clicking on a relevant result. 0.4 probability of clicking on a non-relevant result. And various stop probabilities. What do you see here? Well, you see these 3 curves no longer coinciding. You also see that we don't reach the high levels of performance that we achieved before. And if we look at the table for this very noisy user model, explore even less. Right? The best scores are all the way up there with very little exploration. So the take-home message here is you get your highest improvements with low exploration rates. Apparently there is an interaction between, on the one hand, the noise in the signal coming from the user, and on the other hand, the exploration rate. Okay, so let's sum up what we've done so far. We've looked at a method for balancing exploration and exploitation in online learning to rank. And we've devised this experimental framework for simulating user interactions and measuring online performance. What did we find? Well, you need to balance exploration and exploitation. If you balance it appropriately, then it improves online performance for every click model and all the data sets. And best results tend to be achieved with just very modest exploration rates. Okay, there are lots of questions you can ask about this. We're working with a simulation, so how valid are the assumptions underlying the simulation? Is this the only way of balancing exploration and exploitation? No, of course not. What we've shown is it makes sense to balance them. Okay. Let me now move on to the second half of the talk. And this is about preferences from clicks. So again, we're in this situation where we want to use implicit feedback, clicks, not to infer absolute judgments, but to compare two rankers. Again, we've got two lists, we put them together, the combined list gets clicks. Based on what we observe, we want to conclude which of these lists is to be preferred. Okay, now in the past few years, three methods have been introduced in the literature for interleaving and deriving conclusions from these interleaved lists. What we wanted to do in this ongoing work was examine these and if necessary come up with our own method and somehow understand the differences between these methods.